Hello to all of you on the other screen. My name is Nate Allen, and this is Limits at Infinity in Asymptotes. That means limits are back once again, all the way back from Chapter 2 when we first were introduced to limits and used it to then use our definition for a derivative. Here they come once again, and you may be wondering why. Why didn't we just go over this in Chapter 2? Well, we did a bit right at the end of Chapter 2. We talked about limits at infinity. And now we're going to get into more detail with them now that we know how to graph in more detail and also use limits and derivatives in a more effective way. So hopefully you remember that when we were talking about limits existing, it had to approach the same number from both sides. For a limit to exist as we approach positive or negative infinity, that would then mean that we are approaching from both sides when we go to the farthest right or the farthest left. And like we just got done talking about graphing locally, we don't want to just look in one little window, whatever that is on that screen, whether it's a computer screen or a calculator or any kind of tablet technology. We want to be thinking about outside of that window, right? We want to think outside that box. And so that's what we're going to be talking about as we approach positive and negative infinity. So here's definition 461 that says we're going to come arbitrarily close to some limit as we get really big to the right or to the left. And if you recall, limits were f of x or y values that we were finding. That means they were giving us the x values. So we call these a limit at infinity. So as our x approaches the furthest right or the furthest left, if it goes closer and closer and closer to some number, some y value, we're going to call L, then we say that that limit exists. Now for 462, the next definition, if that's true, if we have a limit, a y value, as we get further and further to the right or to the left, we are approaching some limit, some number. Then what does that mean? We're going to end up having y equals L is a horizontal asymptote of that function. Notice it's just y equals L. It's a line. And let's just say, for example, it was 1 that we were approaching as we went to the furthest right or the furthest left. You can then see that we are approaching some number and it's not going to cross and keep going down or up for that matter if we had another one. This is the namesake of the entire section, limits at infinity in asymptotes. However, will our graphs always approach some number and flatten out, so to speak? Absolutely not. You guys know that, especially with polynomials and many others, of course, but this is just an example. If I had an x cubed, if I wanted to know what the limit at positive or negative infinity was, you can see that it would come out a positive or negative infinity. And it's not always matchy-matchy like that. Positive infinity gave a y value of positive infinity. It could be negative positive. Or if I threw a negative in front of this, it would have gone the other direction. So these are the things that we're going to rehash that we've already kind of spoken about and make sure that we have it so that we can use it all together with the stuff that we just went over in graphing those specific points and values, like critical points, knowing where it's increasing or decreasing, as well as the points of inflection and where it's concave up or concave down. Now we're going to be talking about the far extremes, the furthest left and the furthest right, not just all the key components in the middle. So when it doesn't approach some value like we just went over, we're going to call these infinite limits at infinity. Now, why that? Well, remember, an infinite limit is when our limit comes out infinity, and when it says at something, whether it's as x approaches -2 or x approaches +5. We're saying it's at. We're trying to find that limit at 5 or at -2. Well, now it's at infinity or negative infinity. And if it just shoots up or down in that direction, then it will be what is called an infinite limit as we approach infinity. So that's a lot of words. It's easier to just show you what we mean. As our x approaches positive or negative infinity, our y will approach positive or negative infinity. Infinite limits at infinity, which takes us to our next definition in this section, 463. We say a function f has an infinite limit at infinity if our y value goes to either positive or negative infinity as our x value goes to positive or negative infinity. So this is the verbiage, this is the symbology for each of those infinite limits at infinity. So what is this physically finding for us on a graph? Well, we can say as we go to the furthest right or left, positive infinity or negative infinity, we're going to be finding what is called a function's end behavior. You should have heard of this before. You should have studied this before in either your college algebra or pre-calculus course. But now we have calculus in order to find this stuff as well, even though we don't need it as you've seen in previous courses. So although there's no technical end to most functions, because they have those arrows and it goes on in some form or fashion, indefinitely in either direction, we still want to be able to say what's happening. What is that arrow? Does it flatten out and approach some number we're going to call a horizontal asymptote? Or is it going to shoot up or down forever? Those are the things that we want to be able to figure out, and we want to be able to do it quickly and algebraically without having to graph. So there are basically three different things that can happen in those extreme ends, we call them. Our y value approaches a horizontal asymptote at that limit. It approaches positive or negative infinity, or there's even a special case that happens every once in a while. It does neither of those things in what is called oscillates from one to the next. Can you guys think of a function that you may have talked about or learned in the past that oscillates back and forth? How about sine and cosine? That just keeps pinging back and forth off of 1 and -1 or any amplitude stretch or compression. So there are special cases. Doesn't happen often, but most of the time it will shoot up or down forever or approach some value, some y value we call horizontal asymptote. So as mentioned, we have seen this and studied end behaviors in previous courses. Do you remember what attributes you focused on in those courses in order to figure out what the end behavior was, either to the extreme right or the extreme left? The first thing you should remember is the degree of the equation. The highest exponent in a polynomial will tell you how it behaves based on if it's odd or even. If that degree, that highest exponent is odd, then you know it faces opposite directions. And if it's even, then you should remember it faces the same. Because if the score is even in a game, then you know it's the same. If it's odd, opposite. But there's another important attribute that we need to know that also told us how it would behave, whether it's both up, both down, or from left to right positive or left to right negative ending. And that had to deal with the leading coefficient of that degree. And just like knowing the degree, whether it was odd or even, told us things about the ends, the leading coefficient also, based on if it's positive or negative, told us whether it was even and positive, going to be up and in the same. If they were negative in front of any of those evens, then they would all be facing downwards. Where if they are odd from left to right, it would be positive ending. But if any of these had a negative, then from left to right, they would be facing downwards. And just by knowing the degree and the leading coefficient sign, then you should be able to tell me how these things behave on the extreme ends. And by these things, remember, limits find y values given in x. Well, then what about functions that aren't polynomial in nature? We need to explore what those look like as well. The cool thing is, most of the time, if they're not polynomial, then they will look like a rational or a root, all the things that we've already seen and studied a bit when we were doing the chapter 2 limits. But we're going to review it here now and look at a rational function. Of course, others, but we're going to generalize it with these that are seen most frequently. And I really hope that you remember these a little bit. It'll allow us to go a little bit quicker through the explanations and derivations. But just in case not, go ahead and think about this. Pause it here. Think about if I was to give you some, and we'll keep it very basic to start, rational function where we just have x to the power on the bottom. What if we went to positive infinity for that x? What would my y come out if our power was positive? Greater than 1, not a fraction, no radicals. Well, remember, if you have 1 over a really big number, even raised to a power, whether it was a 1 or anything greater, then you know that when you take 1 and divide it by a really big number, it just keeps getting smaller and smaller and smaller. So small, in fact, that it will never actually reach nothing, because you can see this is definitely something, but it's approaching, hence the limit form, something so small, it's going to look like you have nothing. So that is the result. And whether we're coming from the positive side, approaching our 0 on our number line, or the negative side, you're still going to be approaching that value of 0. So if we just know that, then we can look at a more involved polynomial in looking at a fancier fraction or rational function. So in general, it would look something like this. I know it's nasty, lots of letters going on, but remember, all the A's and B's are simply just the coefficients or constants in front of each one of these variables x. And as always, we like to put these things in what is called descending order, from the highest exponent on down. There are only 3 possibilities, and if you remember what these are already, go ahead and pause it here, fill it in before me, and make sure that you got it down, still from when we went over this at the end of chapter 2, our limit chapter. Otherwise, let's go over it right now, and then I will derive all these with you once more to make sure that you not only remember it, but hopefully even more so now you understand why it is what it is. So let's say that the degree of the denominator is greater than the degree of the numerator. So the bottom degree is bigger than the top. What then would happen if that were true? If the m were bigger than the n, when my degree of the bottom is bigger than the top, well, as we're looking at positive and negative infinities, we want to know generically, not paying attention to all the rest, we'll see why in a minute, what would that be if I ever see that? And of course, let's look at the others too. The numerator is equal to the denominator or greater than the denominator. Simply put, if n is equal to m or n is greater than m, again, just focusing on the degree, the highest power of the top versus the highest power of the bottom. So let's take a look at the first case, which said that the denominator, its degree, was bigger than the numerator, meaning that the m was bigger than the n. Now remember, what we have here is a big rational function, which means I can't change what I actually have, but what I can change is the way it looks. And the only thing that we can do to this fraction is multiply it by a big fancy 1, because we know that anything times 1 is itself. It just may look a little different, but that's still my a that I originally had. So what are we always going to choose? What are we always going to focus on? It, regardless of whether the top or the bottom, the numerator or the denominator is the bigger power, we're always going to concentrate on the bottom. And what we're going to multiply by every single time to this whole thing, everything on it, is that fancy 1 of 1 over x to the m. I'm virtually then going to divide all of the pieces on both top and bottom by x to the m, which would yield this monstrosity after doing that into each one of those. And by doing that, we know that we could then take the limit as x approached either positive or negative infinity. And because all of these, with the exception of this one, would cancel out to be a 1, I'd be able to cancel some of these x's and some of these x's for every single one of these on both top and bottom. But because the denominator was the biggest one, then all of these will have at least one x, because we knew that this was bigger than that. And if all of it canceled up here, and we were still left with some number of x's with all of these, whether it just be 1 or more, we knew that when we plugged in a really, really big number, either to the right or to the left, positive or negative, that it would approach a 0, which means for every single one of these, this would go to 0, this would go to 0, every single one of these would become a 0, as would all of these. So the only thing that would be left in the denominator would be this coefficient, because these canceled out to be a 1. So what would we get on top? Nothing. Everything approached or went to 0. Got so close to it, we're going to say it's next to nothing. But on the bottom, when we added all of these that went to 0 to this that canceled out to be a 1, we were left with whatever that coefficient was, some number, which gave us an answer of 0. Now, if we did that for the other two scenarios to save some time, I'm just going to copy and paste this to get that, and remind you what case 2 said was that what if the top and the bottom powers were the same? Well, now all of the tops would cancel because of the smaller ones, and we'd still have some value of x left in the denominator of all of those, which means all of those would go to 0. But because they are the same here and here, then that means we know that these will cancel out to be a 1 since they're the same, and these would cancel out. And because they are multiplying, then the only thing that's left when we multiply something by 1 is itself, which yields an answer of whatever that coefficient is over whatever that coefficient is, when the numerator and denominator have the same degree. Lastly, case 3 was, what if the numerator was bigger than the denominator? And we did all the same things. Notice why we're only focusing on the highest, because everything else would just become zeros. But this time, the numerator's power is bigger, which means all of the bottom would cancel out, and we'd still be left with at least 1. All of that is always the same. So because all of this became 0 and all of this became 0, we were left with a to the n x to some number, whether it was a 1 or 2 or however many, over just a number. And when we evaluate at infinity, then we will get out a positive or negative infinity. And recall that when we approach positive or negative infinity, those were going to also represent our horizontal asymptotes. So whether we got a 0 when the denominator was the biggest, or when they were the same, they virtually canceled out and we got their coefficients, that would be my horizontal asymptote. But every once in a while, we don't get a horizontal asymptote. And as we mentioned, it will just go up or down forever. So as soon as you see these, you will be able to hopefully just tell me it's this, that, or that, just like we did towards the end of chapter 2. So to summarize all of that, once again, here is my rational function where we got a few stipulations. That's not 0 and that's not 0, because otherwise we don't have those as our degree of our top and bottom. And as we take to find the y value, the limit, as our x approaches either the furthest right, positive infinity, or the furthest left, negative infinity, we can just focus on the highest degree or power of the top and bottom. And if they are the same, we will just have their coefficients. And if the denominator is bigger, then it's going to win. And if it wins as we approach infinities, that means it's going to approach 0 because the bottom won. And if the top wins, then the top is going to go to infinity, which means it approaches either positive or negative infinity. Now we can do a little bit more with that if we wanted. There's a little thing called an oblique or slant asymptote, which means we just have a line, and then we can see what it's approaching, whether it's positive infinity from both sides or negative infinity from both sides as we approach the furthest left or the furthest right. We can actually find that asymptote line, that slant or oblique asymptote that we would be approaching, which gives a little bit more. We can use our long or synthetic division that you hopefully remember how to do from pre-calc or college algebra. There are even some functions that will have rational and radicals involved, and got to be careful with those. Recall that when you multiply by your fancy one to get in and work under a root, you're going to have to multiply by it. Now, there may only be a root in the denominator or the numerator, and not both. So just be careful with your fancy one and making sure it's actually equal to 1. So if you do, for example, a square root of x squared on the bottom, you're just going to do an x on top because we know that this is equal to x. So there is your fancy one. So the last thing I wanted to go over is kind of a synopsis of all of this. How can we combine this section with the one previous in graphing and kind of put it all together? Now remember, the one previous was just the important stuff in the middle, where this is now talking about the ends. So here are 6 steps for you to be able to get a very, very close representation of what the exact graph would look like. First, you should determine what the domain of the function is, or more importantly, any restrictions, things that aren't in your domain. Like with a rational, you can't have a 0 in the denominator, or a radical, you can't have negatives underneath if it's an even root. Okay, things of that nature. It just gives you an idea of the look of it, and if there's any vertical asymptotes and things like that, maybe even a hole. Next, step 2, locate some key points. Not just the critical points or points of inflection, but let's go back to algebra and do things that we've done in the past and locate the places where it crosses through our x and y axis. We call them the intercepts. All you got to do that is let the other letter equal 0. So if you want to find your x, let y be 0. If you want to find your y, let x be 0. And those are typically pretty quick and easy to do, so that's why we find those. Next, this is where we start doing our calculus techniques, where these are things that we already knew how to do in algebra. So what are the new things that we've been talking about? What concept did we learn a lot and do a lot, like a whole chapter's worth? Well, that's starting with limits. And we're going to find those, what we called in this section, end behaviors, by evaluating both the furthest right and the furthest left limits at infinity. And remember, that's finding a y value, which will provide us with our horizontal asymptotes. Once we graduated from chapter 2, which was limits, and we just reintroduce it in this one, we then move to chapter 3, which was all of the derivative stuff. But before we get there, just like we talked about any restrictions, there are other kinds of asymptotes that we called vertical asymptotes. And those are the restrictions on our domain that would not yield a y value. And so we call them vertical asymptotes, which finally takes us to more of the calculus, chapter 3 and 4 stuff, which is to calculate the derivative of our function to find first, remember the first derivative finds those super important, we call them critical points, which if that's where the derivative is equal to 0, then that will also provide us to the right or the left of it are intervals of increase or decrease where our first derivative is positive or negative, as well as our local extrema, or local max and mins, those peaks and those valleys. And once we found our first derivative, we can then use that to find our second derivative to find now all of the inflection points or points of inflection And that was where we found the second derivative equal to 0. And if that's where the second derivative is equal to 0, we can then test around it to find our intervals of concavity. Concave up is where our second derivative was positive. Concave down, where our second derivative was negative. We can even put in our critical points to our second derivative to see if it's concave up, it will have a relative min, and if it's concave down, it will have a relative or local max. So that also helps us to find our local extrema at our critical points. So our goal is to be able to put all of this information together for one goal, and that is to graph as closely as possible to the actual representation of a graph in technology. So keep working at it. Try to put all of this together, really understanding what you're doing, why you're doing it, and what it's finding, and continue to work towards comprehension. I'll see you guys at the next one. Be well, work hard, and enjoy the ride.